We are often taught to identify acids and bases through human senses. Acids taste sour, bases taste bitter. This macroscopic illusion masks the actual mechanical reality occurring at the atomic level. Even our primary diagnostic tool relies on biological reactions. Litmus paper uses a dye extracted from lichen to detect acidity, but observing a color change does not explain the physical mechanism driving it. Chemical identity has nothing to do with taste or color. It is dictated entirely by what a compound does when it encounters water, specifically the reactive ions it generates upon dissolving. This animation shows the actual mechanism of an acid in water. The water molecule chemically strips a hydrogen proton away from the acid molecule. This creates a newly charged structure, the hydronium ion, or H3O+. Watch as the model shifts to a base. The basic compound dissolves, but instead of forming hydronium, it releases a distinct hydroxide ion, OH-, into the surrounding water. This invisible machinery of hydronium and hydroxide generation is the foundational model for the aqueous world. It governs electrical conductivity and dictates chemical reactivity. To prove that water is an absolute physical requirement for this behavior, chemists test how these compounds behave in a completely dry environment. If you take dry hydrogen chloride gas and expose it to a dry strip of blue litmus paper, the paper remains blue. The gas exhibits no acidic properties. Looking at the molecular view, the hydrogen chloride molecules exist as stable, bonded pairs in their gaseous state. Without water molecules present to interact with them, the hydrogen proton cannot separate to form an ion. Add moisture, and the mechanism activates. Water molecules physically pull the hydrogen protons away, creating free hydronium ions, and the litmus fibers instantly turn red. The underlying atomic equation requires two participants. HCl plus H2O yields the hydronium ion and a free chloride ion. An acid cannot act like an acid in isolation. The behavior we classify as acidic is a chemical relationship strictly mediated by water. Since acids produce hydrogen ions, it might seem logical that any chemical compound containing hydrogen would act as an acid. Take glucose and alcohol. Both molecules are packed with hydrogen atoms. If raw hydrogen content dictated acidity, these substances would be highly reactive. We test S structurally by attempting to pass an electric current through separate aqueous solutions of glucose, alcohol, and hydrochloric acid. This circuit diagram illustrates why glucose and alcohol fail to light the bulb. Their molecules remain structurally whole, lacking freely moving charged particles. Shift to hydrochloric acid and the circuit completes. It dissociates into positive hydrogen and negative chloride ions, carrying the current. Having hydrogen in a chemical structure is irrelevant on its own. The compound must undergo the specific aqueous dissociation that frees those ions to move. Once these free ions are mobilized in a solution, they interact aggressively with other materials, starting with pure metals like zinc. Here we see the molecular interaction. The metal displaces the hydrogen atoms from the acid, forming a new compound called a salt. The displaced hydrogen atoms then pair up and evolve out of the liquid as hydrogen gas. We verify the exact identity of this escaping gas by bringing a burning candle near the bubbles. The ignition yields a sharp popping sound, confirming the presence of volatile hydrogen. Introduce metal carbonates to an acid instead of pure metals, and the dissociation pathway shifts, yielding a completely different gaseous byproduct. Routing this new gas through a clear solution of calcium hydroxide, lime water, causes a visible change. The gas reacts to form a solid calcium carbonate precipitate, turning the liquid milky. This specific reaction proves the evolved gas is carbon dioxide. This follows a universal chemical rule. A metal carbonate reacting with an acid always yields a corresponding salt, carbon dioxide gas, and water. The visual evidence, the bubbles, the sharp popping sounds, the milky white precipitates, are the macroscopic predictable signatures of precise ionic displacements occurring at the atomic level. The ultimate test of the ion model is observing exactly what happens when we mix the two opposing forces directly, an acid and a base. This animation maps the mechanics of neutralization. It is not a cancellation of forces. The hydrogen ions from the acid and the hydroxide ions from the base structurally lock together to assemble neutral water molecules. The remaining spectator ions bond to form a salt. Water is both the medium that forces the initial molecules to separate into ions and the final structural product created when those exact opposing ions recombine. To measure the precise reactivity of these solutions, chemists quantify the exact density of this ionic environment. This is the function of the pH scale. The P stands for potens, meaning power. It is a strict numerical measure of hydronium ion concentration. Looking at this dual wedge graph, we see a strict inverse equilibrium. As the pH value moves from 0 up to 14, the concentration of hydronium drops precisely as the concentration of hydroxide rises. A pH reading is a precise count of the reactive ion power contained within a specific volume of liquid. This equilibrium explains why not all salts are neutral. If a salt is formed by combining a strong acid with a weak base, it retains an acidic pH because of the unmatched dissociation strength of its parent molecules. Biological and planetary systems are highly sensitive to these numerical thresholds. Living organisms and agricultural crops operate strictly within very narrow pH bands. Outside these bands, environments become intensely hostile. Venus is shrouded in thick clouds of concentrated sulfuric acid, driving its surface conditions to extreme, corrosive limits. The same limits dictate the durability of human biology. Tooth enamel is the hardest substance in the body, but when the local pH in the mouth drops below 5.5, the calcium hydroxyapatite crystalline structure actively begins to dissolve. From the atmospheric composition of neighboring planets to the structural integrity of our teeth, the mechanics are identical. The release, movement, and recombination of these invisible ions dictate the stability of the physical world.